much, Mary. Thanks everyone at Metro for having me. So great to see so many of you here this morning to talk about research data management and reproducibility. I'll introduce myself. I have a little slide about myself, but just as a reminder, this first part is very much a 101 introduction to the concepts of data management and reproducibility and some of the practices that encompass them that enable those things. In the second part, I'm going to be discussing the services that librarians can provide around research data management and reproducibility. But as I said, I'm Vicky Rampin. I use she or they pronouns. I'm the librarian for research data management and reproducibility at New York University's Division of Libraries. I'm also the subject area specialist for data science and computer science. That actually came later on. So those are newer roles for me, but exciting. So again, a little about me. I'm a faculty member at NYU Libraries in the Data Services Department. I also teach data librarianship at Pratt Institute's School of Information. So that is a course that introduces people to a lot of the different concepts of data librarianship, including things like data management. And in my day job, I help patrons to make sure that their research materials can be used and understood in the future. So that's sort of the goal of data management and reproducibility. That's what we're doing here. We want people's research materials that they're creating today to be understandable to people, including the original person, tomorrow. So I'll go over a little bit of background so we all have the same terms. We know a bit about the motivating factors. Why do we want to invest time and money into these different practices? Then I'll go over them in some detail and then ask me anything related to this. So ask me almost anything. So a little bit of background definitions, why this topic matters. Why do we care about data management and reproducibility? So to first start, data. What is data? We're going to go by the Federal Office of Management and Budget's definition, which was found in their circular A10. This is the definition that federal funders go off of, and I found it really useful to use, especially because a lot of motivation for data management support comes from compliance with federal grants. So the data is the recorded factual material commonly accepted in the scientific community as necessary to validate and replicate research findings, regardless of whether the data are used to support scholarly publications. So this is a really holistic thing. You notice that data is not like a spreadsheet or a database or some text or image files. It's all of that recorded material accepted in the individual's community as necessary to validate and replicate findings. So there are some things that this doesn't include, like drafts of scientific papers, plans for future research, peer reviews, laboratory specimens, like physical things. But it does include, your documentation, your actual, all types of research data. So we're taking a very holistic view of what counts as data. It's what's related to sort of the analytical result or the intellectual result of the work. Research data management then is sort of an ongoing set of practices that help you and other people understand and reuse that work in the long term. And I really love this image from the Turing Way project because, the point of data management really is sort of this wayfinding. You want to be able to take someone from point A, which is like, oh yeah, I read this very interesting paper or article, let's say, and you want to guide them through, how did you get there? What tools were used? How was the data created? All the way through to the analytical results. So this is sort of the point of data management is making each point in this process understandable. So let's see why we care. There's an amazing video made by my colleagues at the Health Sciences Library. So let's see.
Hello. My name is Dr. Judy Benign. I'm an oncologist at NYU School of Medicine.
Hello, Dr. Judy Benign.
I read your article on B-cell function. I think that I could use the data for my work on pancreatic cancer.
I am not an oncologist.
I know, but I think I could use the data for my work on pancreatic cancer. Do you have the data?
Everything you need to know is in the article.
No. What I need is the data. Will you share your data?
I am not sure that will be possible.
But your work is in PubMed Central and was funded by NIH.
That is true.
And it was published in Science, which requires that you share your data.
I did publish in Science.
Then I am requesting your data. Can I have a copy of your data?
I am not sure where my data is.
But surely you saved your data.
I did. I saved it on a USB drive.
Where is the USB drive?
It is in a box. It is in a box at home. I just moved.
But can I use your data?
There are many boxes. So many boxes. I forgot to label the boxes.
Hello again. Thank you for sending me a copy of your data on a USB drive. I received the envelope yesterday.
You are welcome, but I will need that back when you are finished. That is my only copy.
I did have a question.
What is your question? You might find the answer in my article.
No. I received the data, but when I opened it up, it was in hexadecimal.
Yes, that is right.
I cannot read hexadecimal.
You asked for my data and I gave it to you. I have done what you asked.
But is there a way to read the hexadecimal?
You will need the program that created the hexadecimal file.
Yes, I will. What is the name of the program?
Cytosynth.
I do not know this program.
It was a very good program. The company that made the program went bankrupt in 2007.
Do you have a copy of the program?
I do not use this program anymore because the company that made it went bankrupt. Maybe you can buy a copy on eBay.
I have good news.
You again.
I talked to my colleague. She knew a person with a copy of the software.
Then why do you need me? Everything you need to know about the data is in the article.
I opened the data and I could not understand it.
If you have the program, you will find it is clear.
Well, I noticed that you called your data fields SAM. Is that an abbreviation?
Yes, it is an abbreviation of my co-author's name. His name is Samuel Lee. We call him Sam.
I see. And what is the content of the field called SAM1?
Ah yes, SAM1 is the level of CXCR4 expression.
And what is the content of the field called SAM2?
That is logical if you think about it.
What is the content of the field called SAM2?
I don't remember.
What about SAM3? Is there a guide to the data anywhere?
Yes, of course. It is the article that is published in Science.
The article does not tell me what the field names mean. Is there any record of what these field names mean?
Yes. My co-author knows what the content of SAM2 is, and SAM3. And SAM4.
Can I talk to your co-author?
I'm not sure.
I would very much like to talk to your co-author.
Well, he was a graduate student. He went back to China 2 years ago.
Can I have his contact information?
He is in China. His name is Sam Lee.
I think I cannot use your data.
You could check the article to see if what you need is there.
Please stop talking now.
Oh, the dog and panda video. I love this, frankly, because I love this video because it is such a perfect encapsulation of sort of all of the issues wrapped up in managing a complex research project and why we need the practices of data management. And Stephen asked if it's true. It's based on a million true stories. I have seen personally each of these different issues play out across different fields, across different statuses. I mean, there are so many wanted posters in Boast's library for external hard drives that have gone missing, and it's the only place people keep their data. So, you know, these are the types of issues that data management are trying to address. When you think you'll remember something forever and you really won't when you try and keep your files safe or keep any files safe. And I'm using your, but I mean the general you, our patrons' files, our own research too. When we need to make sure that we can read the files after we leave an institution, or we can even open them without relying on a particular piece of software. These are sort of all of the key issues that data management tries to address. And let me go back to my presentation just because there are some examples of these real life data management issues. So this is one example from Cell Biology. And these authors looked at a set of 500 articles that were published in a 20-year time span. And for papers where the author gave the status of their data, like email me for it, or it's on my department server, or something like that, the odds of the data set being there fell by 17% per year. So it's about data that are more than 5 years out tended to be extant. In addition, the odds that these authors could find a working email address for the co-authors, for any of them, the first, last, or corresponding authors, fell by 7% per year. So when we try and even reach out to people, you know, it's tough. And the main point of this article is actually that long-term access to data cannot be reliably preserved by individuals, which I think is true, and we'll discuss more in session 2. But something that the popular media picked up from this is most scientific research from the 1990s is lost forever. This was the Atlantic article based on this study. And it was really interesting because I like this point of lost forever because no one knows where to find it. The biggest issue when these authors emailed other people for their data is that, you know, I'm sorry, it's on a zip disk and I don't have a zip disk reader anymore, or I simply just don't know where it is. So no one knowing where to find it, the issue of storage, the issue of the dog keeping things only on a USB drive is very much drawn from reality, unfortunately. Same with some of these other issues. So this is a very famous snafu, I guess, that happened in research. It has a Wikipedia article about it. It's called Growth in a Time of Debt. It's a very famous economics paper. It was used as evidence for things like Paul Ryan's budget. And you'll notice that this is just by the way Excel works. When you do something in Excel, you can't see the formula. And you can see I highlighted at the bottom there. But you'll notice at the bottom that these folks actually left out a bunch of cells in their calculations. When they add a graduate students at UMass Amherst asked for this data, and when they added in those rows, found that the results actually were very different. So the blue bars there are the original paper, the red bars are the results with the full data set. So you can see this paper was retracted. It was a big deal. It has its own Wikipedia article. You can check it out. But this is, again, when we think of the tools that we're using impacting our research management, it's even sort of the formatting and the files that we're using, or the formats that we're choosing to use. And it happens across all fields. So I've given an example from social science. I've given an example from life science. Here's one from computer science. There are a million reproducibility horror stories and data management horror stories. There is no field in which the research is majority reproducible. Most of the time, research is not reproducible. And that's sort of, again, we'll talk about it in week 2. But once we learn some of these best practices I'll show you today, that's when we sort of start to build services to assist with our patrons. So in this study, they looked at 20 papers across 17 different fields, and there's the list there. They found a lot of different errors, and the pitfalls are listed there. So some of them are in machine learning-based science, or all of them are in machine learning-based science. And they found that these errors collectively affected around 329 papers, and in some cases leading to wildly over-optimistic conclusions, which with machine learning and AI gaining usage makes me a little nervous. So this some of this has to do with our data management best practices that we'll see in terms of managing which data sets we're using. So you'll see on the pitfalls in that table, no train and test split. So that in machine learning, you use two different data sets, a training one and then a testing one, and ne'er the two shall meet. They met in a lot of these papers, and that can bias results quite a lot. So, you know, there are lots of different issues across different fields that can be addressed using data management best practices. So the goal, why we care about doing data management, is to, like, make sure that we are producing research that is valid and can be understood. It should be well-documented research that can be understood without a lot of extra work from the original person. So the idea is that basically you can read this wonderful paper like the panda read the dog's article in Science, but when you look underneath that article, there are so many things that go into it that we need to pay attention to, and that's sort of the tip of the iceberg. So let's look at some of those practices. What goes into managing research data and code on a daily basis. So at a high level, there's kind of 4 key areas of data management. The first is storage and backups. So that's, again, it's sort of the bottom of the pyramid. If you don't have safe storage, you could have the most beautiful data management practices in the world, but if it's all on one USB drive, that could be lost in 10 seconds. You know, what's the point, kind of? So storage and backups are a big part of your data management practices. And again, saying you can substitute researchers' data management practices, but also your own too. File formatting. So again, we don't want to have to buy software in order to read data. So we think about that when we are creating and we're working on our research. Documentation. So human memory will always fail. Documentation usually does not, although it does have to be updated. It is a better fail-safe than relying on memory. And then also some of that organizational piece. So setting things like file naming conventions and project folder setups can really help people make sure that they're using the appropriate data for the appropriate task. This also comes up a lot with qualitative interviews, because interviews go from like audio to an initial transcription to maybe a redaction. And there's just lots of interim files, and the sort of file organization piece of that is really helpful. Would also probably help with those machine learning test and train splits, but yeah. So we'll go into all of these in some more detail so you can get a feel for some of the best practices or the practices that we highly recommend our patrons to follow. So this is the 3-2-1 rule. It's more of a rule of thumb than like a law rule, but it's our rule of thumb for storage practices. So the 3 part is you want to keep ideally 3 copies of a file. So you want to have 1 copy you're always working on, or that your patron's always working on, and then 2 backups. And this is the key part there, and the part that I often have to help my patrons piece out the most is important, because what's important to them might change over time, first of all, and might also be different between collaborators. So this is something, you know, if you have your raw data and your analysis and you can get to the processed data, maybe it's only important to back up those raw data and those tools. So these are some deliberations that kind of have to be made on a project by project basis. The 2 part is 2 different storage media. So it's great that people have like laptops and usually an external hard drive as a backup. Unfortunately, usually people keep that in the same place, like in the same bag. So that's sort of our 1 copy offsite. One of those backups should be in a different geographic location. And this is usually, you know, with a server or with cloud storage. So you might have your laptop and your external hard drive in your backpack, but at least you have a copy of the data on a server. My big example I like to give is, well, I guess I already said the wanted posters in Post Library are always kind of a funny sob moment, like a lol sob moment. But there's also, there's just a lot of them. So we want to make sure that we keep data at least one copy away from us in case of catastrophe. You can do this with like Google Drive or any sort of similar provider very easily, like Dropbox or Box or Nextcloud or any of those. All of these storage providers have desktop applications, and they just show up like a regular folder on your computer, the same as my photos or my documents. It would say like Google Drive or Box or something similar. When you're on the internet, it will sync, giving you your one offsite copy. And then because it's just a folder on your computer, you can sync it to an external hard drive. So it's pretty much a simple way to comply with the 3-2-1 rule. And it's definitely advice that I give to my own patrons when I meet with them. I also always make sure they know that hard drives last 3 to 5 years. You know, they're just spinning disks, so they can wear out. And again, this will apply pretty much to any storage provider, but when I'm thinking about, okay, so if the best practice is a 3-2-1 rule of thumb, what's the simplest way to get people there? And this is one of those methods that gets people there. Barring any questions on that, I'll move on to project structure. So again, this is one of those practices that I highly recommend. A lot of people try to make documentation about their project in a file path. Like you'll have your project main initial, new experiment, good, results 1, keep these, Saturday, cycle 1, and then all the way at the bottom here, you see it gets to the image file. I've seen this a lot, people taking a million clicks to get to the file that they want to show me. I've done this before in my own past. But the issue is once you then try to send somebody that TIFF file, they're not going to have any of the context that goes with that file structure. So as a sort of like check and balance on ourselves and to make sure we know exactly what version of what file we're using, I definitely recommend and it's a good data management practice to use sort of flatter folder structures. And again, this should be something that makes sense for you. I usually don't recommend people to go more than 2 folders deep. There's obviously accompanied by documentation, but ultimately it should be easy for both the person and the computer. So it could be organized by something like file type or by different types of analysis, like on this slide here. Like you could organize by code, data, results, or if you're writing a paper, maybe you'd want to organize it by everything that has to do with figure 1 or everything for figure 2. But you want to make sure you have some thematic high-level grouping that isn't that deep. And this again is important for especially when you get into having a million processed files, like let's say you're editing a lot of images or you have a lot of interviews that you're editing, or you are cleaning a lot of different, or you're processing a lot of different data files into one. Your organization is a big part of how you keep those straight for yourself and for your collaborators. So, you know, data management is sort of these small daily practices that add up, that enable reproducibility and that enable, or that safeguard us against losing research. Just makes things more sustainable. So I mentioned documentation just then, and I do want to talk about the documents that go with research and with research materials. I usually recommend 2 documents when I'm talking about this with patrons. And I love this image again from the Turing way, because documentation really does light the way. I always say past you doesn't write emails. I think it's a common thing and for librarians to say, but it's very true. So I definitely recommend something like a README file when I'm talking to folks. So in your project folder, a README file basically describes the work at a very high level, as well as any dependencies or assumptions. So let's say that this is a qualitative project and you have a lot of interviews. In your README file, you might want to talk about how you've processed those interviews. Did you remove all instances of like all of those, or did you keep them in? Why? some of those decisions, as well as saying all of the cleaned interviews are in this folder, all of the redacted ones are in this, etc. And then, because we don't want to have the issue of something like SAM1, SAM2, SAM3, something like a code book is really useful for defining the specifics of what data are. So the different variables you use, your column headers, what tags mean. So any of the specifics of a particular data file or data set is best put in something like a code book. And ultimately, we're trying to get to this. We're trying to get our patrons to this, which is basically like, I read my README. Now I know that I can run this one script and my analysis can run on its own. And this is from JHU's Data Science Center. I really love this image because it shows sort of all of those things I just talked about. We can see the different folders, separated different types of data. It has great documentation. These are some things that are the markers of good data management practices that also really help with everyday research work. Like it makes your research more efficient as well as more sustainable. Something I didn't talk about is file naming. And again, these are some of the things that are the small daily practices that add up. So file naming is a big part of these data management practices that I go over and discuss with patrons. So you want to have short file names recognizable to humans and machines. So I've said that a few times. Data management is about making things more understandable to people and computers, both. I highly recommend folks to prefix their files with a date. It can be the date the file was created, the date the file was updated. It doesn't really matter as long as you write it down. Want to avoid special characters and spaces, things like that. And you can immediately tell that the difference between the two file names on the side there. I was hoping folks might be able, we could take a little pulse. And if folks could put in the chat, which do you think is the newest version of this plot? You can go off the file name, you can go off the image itself. But if folks just want to put in the chat which one you think it is, I'll just pause a sec and then I'll reveal it. 1 vote for plot final, all right. Another one for the plot final new. All right, 2 for that, yeah. All right, a lot of people think it's that one. 1 vote for plot new, but everybody else has mostly said final plot new and plot final. All right, I'll do my big reveal. It is plot new, the one in the middle. Jen, you're totally right. It could have been any of them. It was a total trick question. There was absolutely no way to tell based on the file name alone. The only way that you could have possibly seen which one was the newest one is the font. These two are sans serif and plot new is the serif of the journal. This is actually my plot that I made for a journal article. So that is the only way to tell. And this just underscores why file naming is important, why we care about it, and why it ultimately helps us. Because when I go to submit to the journal, I want to make sure that I submit the right plot. So it is this one in the middle, but thank you all for playing along. It was a total trick question, so don't feel bad if you didn't guess it. It really could have been any of them. You're definitely right. So another thing I'll mention, we saw in the dog and panda video that the panda had to buy a piece of software to open the data. I've definitely done that. I've definitely had to download random software off the internet to try and migrate data for different patrons. So something that we encourage in data management best practices, so we don't have to do that in the future, is using open, what we call software agnostic file formats. So that's basically a file that can be opened with many different software, not one. So, that's the difference between like a Microsoft Excel and then a CSV file. A CSV file can be opened in Excel or Numbers, which I think is the Mac one, or Google Sheets, but it could also be opened on the terminal in the command line. You can read it there. You could read it in any plain text editor. It's a very sustainable format in that way. So another piece of advice that we give in talking about data management best practices, again, is If you have to use those proprietary formats, it might be a good idea to keep your backups as the more open file format. And a lot of different data types have an open corollary, some do not. Like in genomics research, it comes off the machine in the format it comes off. The machine is proprietary, the format is proprietary, and it can be hard to work with something else. So this is, again, a practice we're reaching for, that we want everybody to do, but acknowledge sometimes it can't be possible. And again, this is just sort of the difference. This is what a docx file looks like when you open it in a plain text editor. It just looks like wingdings. So this is what we mean when we say a sustainable file format. We want it to be openable in lots of different types of software. So for data management practices, these are sort of the main tips. For storage and backup, you want to think about that 3-2-1 rule of thumb. You want to use as open file formats as possible to make research materials more accessible and sustainable. Using consistent folder structure is really helpful for understanding and quickly finding materials in a project. Documentation is necessary for every single part of a research project. Data, code, workflow. Everyone will forget everything, even if you don't feel like it now. So documentation is the #1 most important thing. Setting up a file naming convention can likewise just help you understand and navigate things easier. And working as transparently and automated as possible just minimizes those human mistakes that can happen. So I'm going to talk about reproducibility practices. I'm not going to spend a whole lot of time on that, but it's important to understand sort of the last mile or the things that make reproducibility hard. Like, why is nobody majority reproducible? We're going to find out. Just to define our terms, reproducibility is when independent people use the same research materials and conditions to verify a claim. Replication, by contrast, is when independent people use different research materials that are collected the same way to verify a claim. So in the real world, something like reproducibility would factor in if, like, a reviewer of a paper was rerunning someone's code during the peer review process to double check that the specific findings in the paper match their process. So it's not that capital T truth of the claim. It's like, does your process match what you say? Did you do what you said you did? Trust but verify. Replication is more like someone reads the published paper and says, like, oh, that methodology I think is actually really interesting. I'm going to try and do that same thing again just to see if the findings would be the same or not. So that is about validating that scholarly claim, not necessarily the specific results of that paper. So that's sort of the contrast between them and when they're useful. They're very useful for different things, and they have the same sort of requirements. But those are the different contexts where, those are the different contexts for reproducibility and replication. RDM practices that I just went over will get you 90% of the way to reproducibility. You will not be able to work reproducibly if you don't document your work, if your file formats aren't open, things like that. But there is sort of that last 10% that is just computers make reproducibility really hard. Like going from Windows to Mac, even in a non-research context, even if you're just switching over your computer, is hard. So imagine doing that, also trying to make your results work the same across those different types of computing environments. It's just hard. So there's a great story from Ars Technica here that is an example that I'll give about some errors in Python scripts used for analysis in chemistry. And it's emblematic of this problem called dependency hell, which is basically that computers have so much of like a chain of dependencies that it's impossible for people to get at all of them. And it causes issues when trying to reproduce people's work. So the problem was that a specific Python library that they used called glob returns the results in a different order depending on what operating system you're on. So it's not really easy to tell this was happening. And you can see a quote there that on some operating systems, on Ubuntu and Mac OS Mojave, the intellectual analytical results were off by nearly a full %. And this quote really kind of pulls it all together from the article. This simple glitch calls into question the conclusions of a significant number of papers on a wide range of topics in a way that cannot easily be resolved from published information because the operating system is rarely mentioned. And this is like the dog and the panda. It's all in the article. Like, we know it's not. And this is what makes this factors into what makes reproducibility hard. This is another example of dependency hell with a neuroscience software. Again, just another example from another field. So you can see that it's everybody, it's all software. And that graph shows you again the differences in the results, and you can see they're pretty stark. I really liked this paper from Kim et al. They tried to go from, they tried to reproduce things in using different tools as well as the same tools. So they had different configurations of using MATLAB and Python to accomplish some research task. And they ran into a number of issues. So when they tried to use the same MATLAB code and the same data on a different computer, they found that they couldn't actually, because one of the files was specifically related to the operating system. So they literally couldn't run it on something else. When they tried to convert the code to Python and use the same data so that they could run it on a different computer, they found that because of the differences between the tools, it wasn't working. And it wasn't even just technical issues, but things like what each parameter was supposed to be was not defined in the original paper. There's traces of debugging that just are kind of unnecessary code. So it was kind of a lot to wade through. So I really liked the conclusions that they came to as well, because they mentioned in this paper, the main barrier to reproducibility is the lack of compatibility among these computing environments. At the individual level, the key is those research practices, those data management practices that I just went over. And then at the community level, they also have some propositions, which I'll consider in session 2, which is about services to support this work. But it's just, at the individual level, data management practices will get you 90% of the way there. But then that main barrier is sort of that computational piece. And so this is kind of what it looks like. The article, again, the tip of your iceberg, the code and the data are really useful. You need documentation, and then sort of the last piece of it is the computational environment where all the research takes place. Like, this doesn't matter for some things, like for qualitative research, the computational environment does not matter. For things that rely on software to give you the analytical result, like if you are relying on Python to process an image for you, or if you rely on R to process your census data for you, you are relying on it to give you the result, and the computational environment does matter. So, it's for computational research where this really has an impact. Quickly too, in the last few minutes, I just wanted to go over the different types of reproducibility tools out there. So there's not much, again, that people can really do about these dependency hell problems, except try to address getting those dependencies. So a container is a portable and lightweight operating system that can be shared. And this is something that people use as a part of infrastructure, but it's also used for research purposes. There's things like web-based development environments, like if anyone has seen Jupyter Hub, it basically provides a place to write code in your browser that then can be shared. So everything's in your browser. You don't have to worry about going from different environment to different environment. It's the same thing with web-based replay tools. So if you or your patrons have some data in your repository or on GitHub, they can use a web-based replay tool to rerun and reproduce that work. And then a packager is a tool that sort of bundles together all the research materials with every dependency. And an example of that is something like ReproZip, and it creates a self-contained package you would then share. There are a lot of papers written about how to use containers for research. So I'll just say they are, again, virtual operating systems. They're most often Linux. It's meant to be built and destroyed very often. It's used for short-term sharing. In research, the most popular that you might see are something like Docker or Singularity. And Singularity is particularly used for high computing needs, like you need a lot of compute. So that's what a container is. This is one example from the book, The Practice of Reproducible Research, which I highly recommend. It's a case study by Ben Marwick, who's an archaeologist, and he has a little workflow diagram here on the right that shows how he published 2 different papers using, again, those data management best practices, plus a Docker container to make sure that people are using the same version of R, the same operating system, to make sure that they get the same results at the end. And yeah, so it's all open access. I highly recommend that book and that case study. A web-based IDE, so again, that integrated development environment, this is what it looks like. So you can see this is just RStudio. It's inside of a different platform called Wholetail, and it basically provides researchers a place to do their work and keep all of the dependencies in this one platform. The catch there is that you have to do all of your work inside of that platform, so you can't do it offline, which is a bummer for some people. This example is from Wholetail. Everything, the working directory is /Wholetail. It's made in Wholetail first. If I was to click this, you should be able to see it. Hopefully it will just load. So you can see it has some metadata. It's a list of files. You can see we kind of need those data management best practices, otherwise we wouldn't be able to tell what's what. So there are the data sets, there's that README file, there's a run all file. So that's great, and now I can rerun this in my browser and automatically reproduce it. A web-based replay tool, again, something that gives a link to materials hosted elsewhere and gives you a sandbox environment. So Binder is a really popular example of that. So this is a set of analysis of whale migration patterns that was made in 2013. It uses Python 2, which is not supported anymore. The files are hosted on GitHub, but using Binder, I can actually load those Jupyter notebooks in a sandbox environment with the same Python 2 that the author originally used and rerun it and do whatever I want with it. So it might take a while to start, but that's the replay part of it. Packagers, again, those tools that automatically capture dependencies and computational environments at the time you're doing the research. And you would then use that environment, use that information about the dependencies to automatically set them up on a different computer. So ReproZip is one that I work on, but there's also language-specific tools like Piper for Python or Rem for R. And it's just one of those things you look around for whatever tool or language you're using. Here's one example from a historian. So this historian used ReproZip to package R scripts. If we were to click here, we can see here's that R script. There's all the different data files in various different formats. If I scroll, there's a lot of files. There's those CSVs. If I click the reproduce button, I'm going to see that R script. It's going to build. Let's see, it might take forever for both of these, but I hope not. This is actually also a persistent link, so anybody can come back to it and see how it works. But basically what this is going to do is it's going to let me rerun the script exactly how the original author did it, so that I can see, oh yeah, here's the R plots. Yeah, there's the original plots from the paper. And again, it was like 2 clicks to get to that. So that's the beauty of using a packager. It's simple and it's self-contained. So we have about 10 minutes left, and I'm happy to take any questions. Just as a quick summary, data management is a necessary part of doing research. Data management practices are set up for sustainability and efficiency. Reproducibility tools kind of help with the last 10%, that computational environment piece. And then something I say to all the patrons and something I'd say to all of you too is that these practices sort of, it starts in the mirror, but you're not alone. There are lots of people encountering millions of different data management problems and reproducibility issues. And there's lots of vibrant communities in different fields of research that are working on addressing them, including in librarianship, which again, we'll talk about more in session 2, but this is a good start. So hopefully see you then. Feel free to get in touch with me at any of these places. And yeah, I'm happy to take any questions that folks have about anything.